Meet Michael Faraday, the curious bookbinder turned science star. All right, science fans, let's talk about a super important dude, Michael Faraday. Picture this, it's way back in 1791 in England. Michael Faraday pops into the world, but not into a world of riches or fancy schools. No siree, his family was pretty poor. But young Michael had something amazing, a brain buzzing with curiosity. He wanted to know how everything worked. He was like a little science detective, always looking for clues. He didn't get a formal education like some other scientists of his time, but that didn't stop him one bit. He was determined to learn, and learn he did, mostly by himself. Now, how did our hero get his start in the world of science? Well, it's a cool story. He became an apprentice to a bookbinder. That's someone who puts books together, so he was surrounded by books all day, and what do you think he did? He read them. Lots of them, especially the science books. He wasn't just binding them, he was absorbing all that amazing knowledge. He was particularly fascinated by electricity, which was a pretty new and mysterious thing back then. People were just starting to figure out what sparks and shocks were all about. Faraday was hooked. Faraday didn't just stick to one thing, oh no. His curious mind explored all sorts of science. He made some really big discoveries about electricity and magnetism. You might have heard of electromagnetic induction? That was him. He figured out how to make electricity by moving magnets. Think about that, it's a big deal. It's the basis for how we generate most of our electricity today. He also did important work on things like liquefying gases and discovering new chemicals like benzene. He was a true science superstar, always experimenting and always questioning. His journey into understanding how electricity interacted with materials was just beginning. He wasn't content just knowing that electricity could make sparks or move magnets. He wondered what else it could do. Could it change things? Could it take things apart, or put them together? These questions led him to some incredible experiments with chemicals and electricity. This is where our story about electrolysis really begins to unfold. Get ready, because it's going to be electrifying. He was about to uncover some fundamental truths about how our universe works, all with some wires, some chemicals, and a whole lot of brain power. So, what is this fancy word, electrolysis? Let's break it down. Electro sounds like electricity, right? And lysis means to split or break apart. So, electrolysis is basically using electricity to break chemical compounds apart. Think of it like this. You have a really cool Lego model, that's your chemical compound. And electricity? That's like your special Lego separator tool, but supercharged. It zaps the Lego model, the compound, and carefully pulls the different colored bricks, the elements, apart. Pretty neat, huh? To make electrolysis happen, you need a few key things. First, you need something called an electrolyte. This is usually a liquid that can conduct electricity because it has tiny charged particles called ions floating around in it. Think of it as the soup where the chemical action happens. Then, you need two electrical conductors called electrodes. One is called the anode, and the other is the cathode. Finally, you need a power source, like a battery, to provide the electricity. The electricity flows from the power source through the electrodes and into the electrolyte. Let's imagine we're doing electrolysis with water. Water, as you know, is H2O, two hydrogen atoms and one oxygen atom stuck together. If you pass electricity through water, with a little something added to help it conduct, guess what happens? Bubbles start forming at the electrodes. At one electrode, you'll get bubbles of hydrogen gas. At the other electrode, you'll get bubbles of oxygen gas. We've used electricity to split water into its basic parts. It's like magic, but it's science. This process is super important for many things, as we'll see. Now, Faraday noticed something really interesting. He saw that this splitting wasn't just random. It wasn't like sometimes you got a lot of bubbles and sometimes just a few, even if you used the same amount of electricity. He realized there must be rules governing this process. How much stuff gets split apart? Does it depend on how much electricity you use, or how long you run the electricity for? These were the questions buzzing in Faraday's brilliant mind. He knew there was a pattern, a predictable relationship, and he was determined to figure it out, and boy did he ever. Michael Faraday, being the super observer he was, didn't just watch bubbles. He measured, he experimented, and he came up with some amazing rules now called Faraday's laws of electrolysis. The first big idea is pretty simple. The amount of chemical change that happens during electrolysis is directly proportional to the amount of electricity that passes through the electrolyte. Whoa, what does that mean? It means if you use more electricity, you get more stuff changed. If you use less electricity, you get less stuff changed. It's like filling a swimming pool with a hose. The longer you leave the hose on, time, or the stronger the water flow, current, the more water you get in the pool. Think about it like this. Electricity is like a team of tiny workers. Each little bit of electricity that flows can do a certain amount of chemical work, like pulling apart one molecule or depositing one atom. So, if you send a bigger team of workers, more current, or let them work for a longer time, they're going to get more done. It's a direct relationship. Double the electricity, you double the chemical change. Triple it, you triple the change. This was huge because it meant electricity wasn't just some mysterious force. Its effects could be measured and predicted. It made chemistry and electricity talk to each other in a very understandable language. Faraday's laws give us the exact recipe for how much chemical product we can get for a certain amount of electrical input. It's like a super precise cookbook for electrochemical reactions. This was revolutionary stuff, folks. Why was Faraday's work on electrolysis so groundbreaking? Before him, people knew electricity could do weird stuff to chemicals, but it was all a bit fuzzy. Faraday brought clarity. He showed, with numbers and careful experiments, that there was a direct, measurable link between electricity and chemical change. It was like he gave scientists a new pair of glasses to see the world. Suddenly, electricity wasn't just for sparks and shocks, it was a fundamental quantity that could be precisely related to amounts of matter. This helped establish that electricity itself was likely made of particles, eventually called electrons. Think about some real-world stuff. Ever seen shiny chrome bumpers on a car, or a silver-plated spoon? That's often done using electroplating, which relies totally on Faraday's laws. In electroplating, you use electricity to deposit a thin layer of one metal onto another. Faraday's laws help manufacturers control this perfectly. They know exactly how much electricity to use for how long to get just the right coating. This makes things look good, and it can also protect them from rust and wear. It's precise industrial-scale chemistry, thanks to Michael. And it's not just about making things shiny. Faraday's laws are crucial for producing some very important metals. Take aluminum, for example. The cans you drink soda from, the foil you wrap food in, that aluminum is produced using electrolysis on a massive scale. It's a process called the Hall-Héroult process, and it uses huge amounts of electricity to extract pure aluminum from its ore. The same goes for refining copper to make it super pure for electrical wires. Without understanding Faraday's principles, these industrial processes wouldn't be nearly as efficient or even possible on the scale we see today. So even though Michael Faraday made these discoveries almost 200 years ago, his laws of electrolysis are still incredibly important. They are fundamental to a whole bunch of modern technologies. From manufacturing pure metals and chemicals to the principles behind some types of batteries and fuel cells, Faraday's insights are still at work. He showed us that when you combine curiosity with careful experimentation, you can uncover the amazing rules that govern our universe. And that, my friends, is what science is all about. Pretty cool, right? Science rules.